Hi class, I wanted to make this video to go over again one of the most important things we've talked about this week, which is how to actually calculate the residue of a function at the location of an isolated singularity z equals z0. In the vast majority of cases we're interested in physics, the functions we're interested in are functions with a pole of some finite order n, where n is some integer greater than or equal to 1. And so therefore the function that we're interested in has a Taylor series expansion, f of z, which starts at inverse powers of z minus z0 to the n, where n is the order, and then it has lower singular powers of z minus z0, and then it has a piece that's not singular at z equals z0. But if we look at this expansion, what it means is that z minus z0 to the n times f of z is analytic. That is, that this combination, z minus z0 to the n times f of z, has a Taylor series expansion where the coefficients of the Taylor series expansion correspond precisely to the coefficients of the Laurent expansion of the original function. And in particular, the residue, which is the coefficient of the singular piece that goes like 1 over z0 to the first power, is the nth term in the Taylor series expansion of this modified function. So we can calculate a minus 1 in general if we know that the function has a pole of order n by the usual sort of Taylor series formula, 1 over n minus 1 factorial times the n minus first derivative with respect to z of z minus z0 to the n times f of z. And the limit is that. We evaluate that as z approaches z0. So this is the general formula for how to compute the residue of a function f of z that has a pole of order n at location z equals z0, and it depends on the value of n. In many cases, we're interested in the special case of a function with just a simple pole. There's an important special case that we emphasized that I want to remind you of, and that is in the case of a simple pole, so n equals 1, a minus 1 is just the limit as z goes to z0 of 1 over 0 factorial times no derivatives of z minus z0 f of z, which is to say it's just the limit as z goes to z0 of z minus z0 times f of z. Often, we're interested in a case where f of z is the ratio of two things, a function g over a function of h, where h has a simple 0. By simple 0, we mean that the function vanishes at z equals z0, but the derivative of h at z equals z0 does not, and where the numerator doesn't vanish at all. In that case, since this has a simple 0, the function f of z has a simple pole at z equals z0. Then a minus 1 is the limit as z goes to z0 of g of z over h of z times z minus z0, and we can just use L'Hopital's rule, which tells us if you have a function that vanishes in the numerator divided by a function that vanishes in the denominator, the limit as z goes to z0 is just the derivative of the numerator divided by the derivative of the denominator in that same limit. But if you take the derivative of the numerator, there's one term where you take a derivative with respect to that gives you a g of z0, and the other term, which would be the derivative of g times z minus z0, vanishes, and then in the denominator you have the derivative of h with evaluated at z0. So in the case of a simple pole, where the function can be written as the ratio of g over h, where h has a simple 0 and g is not 0 at z equals z0, then the residue is the value of the numerator divided by the derivative of the denominator. This is an extremely useful special case that we will see over and over again. References for this short talk can be seen in the book in Leah section 2.6.3.